Welcome back to our episode 2 of the Terraform series. And today we're going to step up from the basics that we learned into a more intermediate lesson, where we will focus our attention towards programmatically approaching Terraform. Because Terraform is surprisingly rich with capabilities. And to showcase those capabilities, we are intentionally going to over-engineer our project today. Not because it's how I recommend writing every part of Terraform at work, but because it's the best way to explore what the language is capable of. And we'll explore many topics ranging from Terraform function, which allows us to transform, manipulate, calculate values without having to hard code everything ourselves. Whether it's formatting text, working with IP addresses, combining data, functions become one of the most common tools you will use in Terraform. We'll look at loops, where instead of writing the same resource over and over, we can loop them to generate multiple resources from a single block of a resource. I'll showcase the different kinds of loops, when to use each one, and the trade-offs between them. Then we'll explore expressions, including for and splat expressions, to transform, reshape, and retrieve data exactly how we want it. Beyond that, we'll introduce conditional logic, which allows us to make decisions like an if statement, like whether a resource should be created at all based on values we provide or not. And to support that logic, we'll explore operators. Operators allow us to compare values, combine conditions with ands or ors, and build more advanced logic throughout our configuration. We'll also expand on validation. Rather than allowing invalid values to make it all the way to Azure, Terraform catch many mistakes before deployment even begins that we set. Here we'll cover the newer validation features as well, such as preconditions, postconditions, and check blocks to verify assumptions through the deployment lifecycle. And then we'll work on collections deeper, such as building on these collections with nested type. Because as projects grow, simple strings and numbers aren't enough. Lists and maps aren't even enough. So we'll learn how to organize our related information into structured objects that make our configurations far more powerful and reusable. And then there are dynamic blocks that allow us to generate nested configurations in our resources without having to write repeated code either. And as we're going through this, we're going to work through meta arguments, which are features such as lifecycle, count, for each, and provider, which give us much greater control on how our Terraform creates and manages our infrastructure. Including in that is the aliases for our providers, so that we can allow a single Terraform project to deploy resources across multiple Azure subscriptions, which we did not cover last time, and much more that you'll see sprinkled out through this episode, including several topics that are considered intermediate Terraform, even if they're not strictly programming concepts. So yeah, these are capabilities you simply don't get with ARM template, and is one of the reasons Terraform has become so popular. So settle in, this is going to be a fairly information dense episode, but I'll build that complexity gradually, so each concept naturally builds on the last. With that, let's begin. And we're back. Let's begin by setting up our new file, main.tf. I'm going to do it in a new folder, main.tf. And let's make sure we cd into it. The first thing I'm going to add into our main.tf is going to be our Terraform block. And before I add the version, let's actually talk about that here. In the beginner episode, we hard-coded an exact provider version and set a version to be equal to something. And that's perfectly fine for learning. But in real projects, you will want something a little more flexible. Terraform supports version constraints, allowing us to automatically receive compatible provider updates while avoiding unexpected breaking changes. So if we wanted to set our semantic version to be equal to, like we did in the last episode, we could do that. If we want it to be greater than a version, we could do that. We can even provide a range where we want it to be one version to another and nothing else. And then there's something called pessimistic. So for this series, I'm going to use the pessimistic version constraint. And I want to mention this because you will see this in different Terraform configurations, so might as well get used to it. And the one I've written just allows Terraform to use compatible minor versions while preventing upgrades to the next major version to take place. So this will never go higher than 4.0, 4.x I should say. And that's because major provider releases can introduce breaking changes. So this gives us a little bit of a safety net. And when you are ready to upgrade to a major one, you should definitely test it out because some things are going to shift. Some verbiage is going to change, or something's going to get removed, something's going to get added, etc. Next, let's configure our Azure RM provider in its simplest form. Writer, Azure RM, features, empty. This time, I won't use Azure CLI. Instead, we'll authenticate with an app registration. Since we're learning Terraform, how about with each episode, we try a different authentication method? So the next episode, we'll try managed identities. The one after that, we'll try federated credentials. So that by the end of it, you know all the ways you can auth into Terraform. And what we will do, I have an app registration in Azure, and it's called SPIT Terraform. And it already has the RBAC permissions needed to deploy all the resources that we're going to work with today. So if you're going to make one, make sure it has the permission. And I'm going to use a secret, not a certificate, just to make it easy for our lesson. I already have it generated and it's already stored in my key vault. So we will place our authentication details directly in the provider block, which if you look at the doc for it, scrolling down, is essentially this. So we could place our authentication details directly in the provider block as you see right here. Not just our subscription ID and tenant ID like we did in the last episode, but also our client ID for our app and its secret. We could move these values to variables where we either enter it during runtime, which would be annoying to do, especially for long secrets, or store them what we did last episode, which is TFVAR files, which still leaves us with a secret sitting in plain text. So instead, let's explore the one variable method we didn't touch the last episode called environment variables, as it is a common and more safer way to provide sensitive information to Terraform. So environment variables are values stored in your current terminal session, either by PowerShell in Windows or Bash in Linux. And once the terminal closes, those values are gone. While these environment variables for your terminal aren't exactly for Terraform, during runtime, Terraform actually checks for the environment variables automatically. All you have to do is set specific environment variable names that it would look for with the values that you set. If it finds those names, it will use those values. And it's not just for Terraform variables that you write in variable blocks. The settings in Terraform you can configure in environment variables as well. If we had a variable in Terraform to use the format tf_var_variable name, aka sub ID. And then after, if you run the Terraform commands to deploy your services, it will pick this up and automatically populate the sub ID variable. So first, let's set up our variable for our subscription. I'll do variable sub ID, and then I'll do a type equals string, and then I'll do default, and it's going to be one of my subscription. And then in my provider, I'll say subscription ID equals var.subid. Now, even though I just talked about environment variables, I'm actually not going to make this subscription ID into an environment variable because I'd rather keep the subscription ID in my .tfvar file so it can change depending on our environment being prod, dev, etc. But for everything else that we're going to put in this provider, let's use environment variables. Now, I mentioned earlier, environment variables aren't just for Terraform variables like this either. Provider settings you actually configure in your providers, like the subscription ID, tenant ID, client ID, etc., they can be directly set, in fact, through environment variables. For example, the Azure RM provider can be supplied using arm_provider argument. So if we have tf_var, it's for a variable block, but if it's arm_, it's for a provider setting for our Azure RM provider. So let's do that. So because my terminal is PowerShell, I'm going to type env like this, go to colon, and type arm_client_ID equals, and I'll provide my values that are here for my client ID. Copy that, and then let's put quote, paste quote, and hit enter. And I'll do the same for my tenant ID, which is also on the screen. Now, these environment variables are primed to be used by our provider block. For our secret, it's in a key vault. So I will use AZ login just now, just to log in as myself, so I can retrieve that. So you don't see it in plain text. So I'll just quickly run some AZ commandlets. AZ login, sign in. And once I'm signed in, I'm going to run this particular commandlet to retrieve a secret from key vault. AZ key vault secret show. It will store that. And now what I could do is env arm client secret equals the variable secret. and it's stored. Now, because said, I'm not going to use the AZ login this time to work with Terraform. I will sign out of it just to prove that I'm not using it. Now, what's even more interesting for environment variables is that it doesn't stop here either. They can even be set for Terraform CLI commands arguments. For example, in the beginner episode, we always mention an out file when running Terraform plan to store a plan file. We can actually make that a default in our environment variables. So if I go env tf underscore CLI args for arguments, and then what command? It's plan, and I just put the argument that I would have normally typed with tf plan. So it'll be out equals tf.plan. Now I don't need to mention this when I run Terraform plan. It will automatically get added to that commandlet. And I can do the same for apply, because apply, I want to have it read that tf plan. We'll do tf CLI args apply equals tf.plan. And that will be the same. And this is true for any command. So if I do Terraform plan with a help command, there's all these arguments that you can provide. You can make them the default. Another good one, just so you know, is parallelism equals n. This is how many concurrent operations occur at any given moment. So in the last episode, I said that when you try to make multiple resources, if they have no dependency, you'll create it at the same time, right? This is how many you can create at a time, 10. So if you want to expand that, if you have the compute power on your computer, you can do so. If you want to reduce it to one at a time, you can also do that. So it's pretty cool that you can configure your Terraform to behave a certain way by providing these environment variables. Like right now, I'm just typing them. But if you had this in a pipeline, part of the pipeline before it runs any Terraform commands, it just runs all these environment variables into your container or your VM. And then it's designed to work the way you want it rather than the way Terraform expects by default, because it will just pick it up from the environment variable. Now, if you ever want to view your environment variables, depending on your terminals, different commands. So for PowerShell, it's get child item env : and they'll list it all out. And you can see right here, tf plan and apply arguments that are provided, written here. My client ID, my client secret, my tenant ID, written in plain text. I'm just covering it. As soon as this terminal closes, I close VS Code, or I just press this button to kill the terminal. These are gone. So why don't we start? Let's do Terraform Init and get our providers installed in this folder. Cool. And then if I do Terraform plan and make sure everything is working order. Okay, cool. There's not much being created, so it's really quick. But look here, tf.plan. Either way, let's begin on working Terraform programmatically. And we'll start with what I teased in the last episode called functions. Functions are built-in pieces of reusable logic provided by Terraform. They take one or more values as inputs and return a new value as an output. They allow us to transform, manipulate, and calculate data. Some functions work with text, some work with numbers, others work with collections, even letting you set dates, not to mention assist you in subnetting, and much more. The syntax is as follows. Functions are typed by their name followed by parentheses. Inside those parentheses is where we provide the data the function will work with, which will be unique per function. In fact, functions can be combined together and nested within one another, meaning we can place one function inside another function, allowing the output of one function to become the input of another function. The innermost function will trigger first and work its way out. Terraform includes over 100 built-in functions. You don't need to memorize them all. Many of them are functions you may never use. The important part is understanding what they can do, so that you can reference the documentation to find the right function for the task that you're trying to accomplish. So let's see some of the more popular ones you may encounter in action. Okay, so now rather than building a large Azure environment just to demonstrate functions, let's explore them using locals and outputs first. This gives us a quick way to experiment and immediately see the results. We'll use many of these functions again later throughout the episode. Let's just start with a simple local and an output and just play around. I'll do a locals block, and in here I write region equals Canada Central. And then I'll do an output equals our outputs. And then in here, I'll do value equals map. Made a mistake. Let me remove this. Now I'm just going to make one monolithic output block with maps so that we don't have to write a whole bunch of output blocks separately. So I'll do region equals local.region. Right, easy peasy. I'm going to read into this and output it. Confirm with a plan. There it is. Now let's go to a document. So in Terraform's document itself, you just search Terraform function. You'll come to a page where it tells you pretty much all the things we're going to be playing with. But if you scroll down, you'll see a section called functions. In here, there's so many different kinds, right? So if you wanted functions on manipulating numbers, there's a whole bunch. String, there's a whole bunch. Collections, whole bunch, and on and on and on. And then you can open them to read up about them. For example, I click upper function. It converts all case letters into uppercase. Pretty self-explanatory, so there's not much here, but if you click some of the more complicated ones, it will tell you more about it, kind of thing. But why don't we explore this upper function, as it's a pretty simple one to explore. I'm going to remove the Canada Central part. I'm just going to do a cut so I can paste it later. In order to write functions, you just type their name. So this one was called upper, and look, IntelliSense is still here helping us. Not only that, it will tell you how it works. So upper, put it in a string in there, and it will uppercase all the letters. Straightforward. And after you type the function name, it will have a parentheses. Within the parentheses where you write the data that you want the function to manipulate. So I'm just going to do Control V to bring back Canada Central, and it's going to be inside this upper function. Let's run plan again. Look at the output now. It's all capital like before. And let's do the opposite. I'm just going to replace upper with lower. That's what it is. And run plan. And now it's going to lowercase everything. So the capital C's are gone. Earlier I mentioned that functions can be nested. So let's wrap upper and lower. What I can do is I can put this whole thing in parentheses. So now this is part of another function, which is called upper. Just to make some spaces so it's a bit more clear to see. So we're using an upper function, and inside that we have a lower function. What's going to happen first? Like, are we going to get uppercase letters or are we going to get lowercase letters? One plan. We're going to get uppercase. The idea is the innermost thing occurs first. The string gets written or outputted or whatever. And it gets outputted to a lower function, which gets outputted to an upper function. So Canada Central with capital C's come in, becomes lowercase, which becomes uppercase. So if you're ever trying to read nested functions, go from the innermost part and work your way out, and you will understand what it is doing. And we can use multiple functions in the same string as well. So we touched on string interpolation in the last episode, which was when you have a string, you can do a $, curly braces, and now it's something you can put in programmatically, right? So I can write upper and just say the word Canada. And then after the curly braces, I can hit space, which will be a space in the string, and then do another one. This one I can call lower, and then I can call this central. And if I run plan, Canada's uppercase, central is not. In the last episode, we did tease a few functions. I'm going to mention them again as well. Go back to Canada Central. Now, what if I wanted to replace something? For example, the space here, I don't want it. Like someone may write it in a variable, it comes in, I want to remove the spaces, or I want to change them to something else. What can we use? We can use a replace function. Now, unlike the other one, where you just provide a string, this has a few areas where you can actually put data. So you provide a string itself, a substring inside it, and then a replace string that you want to replace a substring with. So let's just put this in parentheses, comma, and now it's the substring part, and it's cool because it kind of highlights what stage are you on in the replace. So I want to replace the empty space, comma, and now I want to do the replace string. And if I run Terraform plan, it's all one word. If I wanted to have multiple dashes, I could do that, and it will have that extra dash in the middle, wherever it is that we want to replace whatever. Now let's look at another string manipulator called split. This breaks a string into multiple pieces. So I'm going to remove this and type the word split. Now, what's interesting about this one is that it wants the separator string first before the string it is that we're separating. So while replace had it before, this has it after. What I'm trying to highlight is there's no uniformity with the functions with Terraform. But what it is I want to split on the empty space, comma, I'm going to split Canada Central. And let's do Terraform plan again and turn our string into a list. So the first item in our list is Canada's. The second item in our list is central. And since it's a list, we can reference individual items using index, right? So I can put a 0 in our output and run plan, and I should only get back Canada. Okay, let's create another local now, and I'll call this allowed environments. And I'll make it into a list. I'll say the first item in the list is prod. The second item in the list is dev. Now, if you want to turn this list into a string, make another output called joined env equals join. the function. And this wants the separator string and then our list. So what it is that when the joins do I want to have in between all the list items, it's going to be a space or space. And then I'll do a comma, then I'll provide my local.allowed env. Let's do an output, see what happens. There it is. Join env, prod, or dev, right? Something that could be useful when you have a list and you want to do it as an output in an error message for your validation. In fact, let's do that. I'm going to take this output and put it in my locals because locals can read other locals into them. And then I will do env error. So this could be an error message. And let's just say you are not allowed to set env to local.join env like that. And if we run plan, that's the output. Now let's revisit another function that we use in the beginner episode called contains. I'll make another local called allowed regions equals list Canada Central, comma, Canada East. And then the region here, I'm going to actually say is Canada North. Now in our outputs, let's just do some calculations for it. Let's say allowed region, just the name of our value, doesn't matter. And we can do a function here, contains. What it wants is a list and what it is that we're trying to find in the list. So I can say local.allowed regions, comma, local.region, and run plan again, and we get a true or a false. So it's checking, does this list contain this region? No. I'll give you a bool, which is false. Again, which is great for validating, right? Next, let's look at lookup. Lookup searches a map or a key. If the key doesn't exist, it provides a default value. First, let's create our map. I'll call it region underscore codes equals Canada Central. And what is it going to be valued? CC. Canada East, CE. And then Central US, which is going to be CU. And just to give you a tip, if you ever do type uppercase letters, maybe you don't want it to type that, and you're like, oh my god, I have to go to each character and do it. You have capabilities in VS Code. So if you open the command palette, Control-Shift-P, you just type the word lower, and it'll say transform to lower. And look what happens when I hit enter to all the values. Lower cases then. The same is true for upper, right? If you're just quickly working with stuff and you want to modify it, you can do it like that. Now let's retrieve one of these based on what our region is set to. So we can say region short equals lookup local.region codes, comma, Canada Central, otherwise unknown. And let's do plan. And we should get CC back. Oh, lowercase. Canada Central, lowercase, and run plan. Okay, there we go. CC. Maybe wondering, why not just reference the map directly, right? Like we could just do this. Region short via map. Without using a function, we can just say local.region codes equals Canada Central. And if I run that, works, right? We could just do that. Now, what if this value wasn't one of the values we actually wanted? So I have this local here setting to Canada North. Why don't we do this? Because someone's going to input a region somewhere, and we're going to try to get a short form for it. And if it's not there, what do? Well, let's do this. So see what happens when it's Canada North. If I run plan, it fails. And it fails on line 38 because it was not able to find that code for Canada North. Whereas if I comment it out and run that plan, it will work with an unknown value, giving us a way to handle this in a non-terminating way. So while we are working with maps, let's look at some ways to collect data from it. We have keys and we have values, right? What if I wanted to collect all the keys and use them in some way? I can say keys equals keys. Input map would be our local.region codes. And the same could be done with values. So if I do value equals value, S, I think. Yeah. Local.region codes. If I run plan, we'll get both of them as separate lists. So if for any reason you wanted to get the list of the names or the list of the values, you could do that. Another common scenario is using functions to build resource names. Let's start with a hard-coded value. And I'll just do it in outputs. The resource equals rg prod cc001. And let me just comment out all of these. If I run plan, that's all we're going to get output. Sure. Now we could use the locals that we have to build the same string And we've done this using string interpolation before. So the word prod is here, and our region is here. Also make this lowercase. Make this Canada Central. For prod, I can do $ this and say local.allowed env, and I'm just going to put it as 0, so it's prod, but you can have it more dynamic in other ways. We'll see later. And then for region, we can just use our region code. So we can say region _ codes, and because it's a map, we can actually reference a key, which will be local.region. So it'll be Canada Central DC 001. And if I run plan, we get the same output. And I'll save this as string via this. So if I run plan, these two are exactly the same. Good. There's a third way we can do this called format. And let's do that. So we'll say resource via format equals. Instead of doing string interpolation, we can just say format, and then we can provide the structure that we want, like this: rg %s %s001. We use %s as a placeholder for strings with format. So we could now say local, but we can actually copy these here, copy this, paste that. Terraform plan, exact same result. So inject this into this, inject this into this. It makes it a little bit less cryptic, especially when with string interpolation it gets extremely long. So you can see the full format and then you just map it out after the fact. Up to you which you prefer. While we are looking at format, let's look at another use for it. So we have the number 001. Why don't we create a suffix variable called suffix 001, a number? Rather than adding it to this, let me just comment these out and let's actually do it on the resource. A little bit more clear. And we'll just do string interpolation again and say local.suffix. I've set it to 001. Watch what happens. When I run plan, we get it as a 1. So the leading zeros in a number get omitted when you use it in Terraform. And this is where format comes along. And I don't need to format the whole thing. I can just format this one section because this is all I'm really using it for. I'm just going to put the local suffix in parentheses and type the word format in front of it. And right before local.suffix, we're going to provide a special little character. Rather than writing s here for string, we're going to write %d here. And if I run plan, the same. But right between % and d, I can write 0, and then I'm going to write 3. How many zeros? So if I run plan now, we get 001. If I make this 3 into a 5, it's going to become 5 numeric values, including the 1 itself. In essence, saying how many numeric spaces we want this format to occupy. And if I go back to 3 and I make this 999, it's going to be 999 because that's the amount of spaces we're giving it. 3 spaces, right? So what happens if we add another number and make it 4 numbers? And on plan, it will accept that. So what does %03d mean? What does %s mean? Dive into it. The format function lets us build strings while controlling exactly how values are displayed. So instead of simply inserting values, we can tell Terraform how we want those values formatted. Our Roman pacifier always begins with the %. Everything after the % tells Terraform how to display the value. For example, %03d. % means formatting instruction. 0 means pad the values with leading zeros. 3 sets the minimum width to 3 characters. And D formats the value as a decimal integer. And then earlier we used %s. S simply tells Terraform to format the value as a string. This makes it behave similarly to string interpolation. There are many more formatting pacifiers than the ones we've shown here. In practice, you're most commonly going to use %s for strings and %d for integers. The others are useful to know, but you'll most likely only reach for them when a particular scenario calls for them, unlike these two that are going to be pretty common. So those are like the generic functions, right? Pretty straightforward. You can manipulate your data in certain ways, whether it's strings, numbers, lists, etc. Let's look at more specialized functions, starting with datetime. This is something we commonly see with tags. For example, if you want a creation time tag when a resource is created, we can use, I'm just going to skip the locals and just do it in the output, timestamp. This is a timestamp that returns the UTC current time. We run plan again, Terraform plan, our output doesn't show because you actually have to run Terraform apply. And there it is. And by the way, notice that Terraform apply never asks for us to approve because it's just reading through the plan, just like the plan file was automatically creating it. So there is our output, and it's in this format. But this format may not be something you want. Maybe you want year, month, day, space, hour, minute. What are we going to do there? Can't do anything with timestamp itself, but you could use another function called format date. So we want this function to run, and then wrapping around this function is format date. Let me just write format date first, and then it wants the format that you want written in string, and then the time string. So the time string follows our string, and our string is going to have year, 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 month, month, day, day, space, hour, hour, minute, minute. This is a very common formatting method that a lot of languages use. It's the same that applies here. So Terraform plan. And if I do this, I'll have to do apply again. And there it is, 2026 07 06 with the space and the hour and the minute, just the way I wanted it. This is something we'll come back to later when we start using it in tags. But let's continue on and look at networking next. Comment this out, and let's add this to our output. Subnet equals CIDR subnet, another function, and it wants the prefix of our subnet, aka our network address, followed by new bit number and a net num number. If you don't know what those mean, I'll just say the simple form of it. So let's just put our network address. So pretend this is our VNets IP /16, right? And we want to take a /24 from it. The new bit just means whatever number is in the prefix, add this number to it, and that is the subnet size. So if I want a /24, 16 plus 8 is 24. So I write the integer 8, comma. So the net num is basically your position in the subnet. If nothing has taken space in this subnet already, I can write 0, and that would effectively make this 10.0.0/24. If I put 1, it will be 10.0.1.0/24. Understand what I'm saying? Maybe visually it'll make more sense. Let's do Terraform plan. And there we go, 10.0.0/24. Pretty cool. We gave a Terraform a network address. We told it how large of a subnet we wanted and at what position, and it gave us back that value. So this is something I can add to my subnets. So if you wanted multiple subnets, for example, let's call this subnets. Let's make this into a map. Call this subnet A. And I'm just going to put 2 more of these. Get Terraform formatted. Terraform FMT. Terraform FMT. Okay, much better. And then I'll call this B, and I'll call this C, and I'll change this position to 1, to 2. And if I do Terraform plan, we'll get 3 different subnets from this function. But not every subnet has to be the same size, right? /24 is just common, but sometimes you need less for a particular subnet where it's going to occupy that space just for this one particular task, and you don't want to give it too much space for that and waste a whole subnet. So we can adjust that as well. So as I mentioned, these are the sizes. So I can do 9, I can do 11. So if I run plan now, we'll get different sizes, but there is a problem. It's not smart enough to know when this ends and this begins. It was easy with /24 because that was hopping 256 network spaces, but now all of a sudden we're saying this is hopping only half of that. This is hopping only a quarter of that. So you will have to then calculate and figure out, okay, this is 2 spaces away, and this is 12 spaces away from the starting position because it doesn't know the context of anything else. And if I run plan, now there's no collisions happening between them. They're actually sitting where they should be, right? /25 begins at this point. Like at this point, you're pretty much calculating subnets in your mind to get the positions. But there is something we can also use here called CIDR subnets with an S. So I can say subnet second. Let's just call it second. And then I can use that function, subnets with an S. And then what I can provide is very interesting. We provide the same network address, 0/16, comma, and all I provide is the new bits as a list. I can say 8, 9, 11, keep going, 8, 10, 9. So I want, and if I run plan, it will automatically do the exact same task that we're trying to do here, and then continue on how we want. So different sizes will all fit in here. Each subnet is calculated after the previous one, and then you can reference the subnets using indexes, the first subnet, second subnet, third, and on. And before we move on, there's one command worth knowing, and it's called Terraform Console. Think of it like an interactive sandbox for Terraform. It lets you test functions and expressions instantly without modifying your configuration and without repeatedly running Terraform plan and applies like we did just to see the outputs. To start it and see it in action, all you do is type Terraform Console and hit enter, and you will enter an interactive prompt. And every valid Terraform expression you type is evaluated immediately. Let's try one that we did earlier. Lower, Canada, Central, close, hit enter, right? It just gives you the output. Format, %06D, comma, 7, right? Same with a CIDR subnet, CIDR subnet 10.60.0.0/16, 8/2. Like, this is a fantastic place to experiment, test expressions in seconds, and then just copy them into your Terraform configuration once you're happy with the result. And to exit, you can either type the word exit or hold Control and press C, and it will take you out of the console and you're back into the terminal. And that wraps up our quick tour of Terraform functions. We covered the most common ones, but there are many more functions available. We'll continue using functions as we build the rest of this project. For now, I'm going to remove the output examples. And then I'll keep some of the locals we're going to use going forward. Let's build some variables and explore validation a little further using functions, starting with our environment variable. I'm going to make a variable called environment. Type will be string. And then validation, do a condition equals, come back to that. And then we'll do error message. We'll just say must select environment, prod or dev. And as I had mentioned in the previous episode, the conditions only accept a true or a false, but we don't have to write true or false itself. We can calculate an expression that results in either true or false. There are many functions that can help us with this. In the last episode, we used something called contains. This time, let's try something different called anyTrue. anyTrue. And as the name implies, if any of the values that are going to be in this condition are true, we'll accept it. And I'll just set it as true. I'll make it multi-line with just a little bit more easier read, which you can do whenever you have parentheses, by the way. And I'll make the first one var.env equals prod. So if the environment is prod, great. Otherwise, if the environment is dev, also great. But anything else, it is not going to be true. Now notice the two equal signs I used here, unlike condition, error message, and everything else we've been working with. It means equals to. It is not assigning a value. Equals to is an operator. Now, operators allow us to compare values and build logical conditions. Every comparison we make eventually evaluates to either true or false. They become especially useful in validation, conditional logic, and expression. Anywhere Terraform needs to make a decision, you most certainly will find operators involved. For example, you can check if something is equal to another value, if something is not equal to another value, if it's greater than another value or less than. And then we also have logical operators such as and or to combine multiple conditions together. And finally, we have the ability to say not something as well, where we invert the result of a condition. And all of these open us up with so many ways to approach our condition. So let's run Terraform plan. And because I don't have a default, it will prompt us. And let's type Bob, something that is not in the condition. Validation fails. Run it again. Type prod. Validation still fails. What have we done? Oh, I know. Forgot to encapsulate it into a list. Because we're providing multiple values, we got to use the list block with square brackets. If you don't, we're saying it's a string and it doesn't make sense to have this be a single string, right? Okay, that makes more sense. Let's do plan again and type Bob. Failed. And now we actually get our error. Okay, now if I type prod with plan, it works. Like it implies anyTrue, there's another function called allTrue. With allTrue, everything in the function must be a true value. Environment must equal prod, but it also must equal dev. Doesn't make sense here, but I'll show you another example of that another time. Now, if I wanted to inverse this, meaning it can be anything but these two values, I just put an exclamation mark right in front of the function like that. Now I'll accept anything besides these two values. So if I run Terraform plan with Bob again, it will work. If I run it with prod, it will fail. Let's remove the exclamation mark and move on. And I think we can improve this programmatically, in fact. Right now, we're repeating this pattern over and over. var.env equals prod, var.env equals dev. Now imagine if you had 10 or 20 of these environments. Writing this would be very annoying, not just to write, but also to maintain. Let's just make it a little bit easier. And this is where contain exists. So we can just say contains the function, put in our list. And in our list, we can write prod, comma, dev. And then after the list, we can do a comma and say var.env, eliminating the need for us to write var.env twice, or 10 times, or 100 times. Now, if I simply wanted to expand on this, I could just add more things into the list. Let me just run Terraform plan and just do prod again, just to make sure we're working. It is. And if I wanted to add more and say UAT, I can do that. And if I run plan and type UAT, that will now work as well, but not Bob. In fact, we can still do better than this, because right now, you just saw when I type UAT, 1, our error didn't even mention it. And 2, I have to write it here, and then I'll have to write it here. So we're still repeating, still not dry enough. So what can we do is something I've already hinted at in our locals and allowed environments earlier. Let's just reference them. So in our allowed environments, let's just add UAT. In our contains, let's just replace the list here with our local.allowed env. Our environment here, let's just use a join operator because it's a list and we want to make it into a string for the error message and say join it with a comma, what are we joining? Allowed env. Now if I run plan, it should behave the same way. If I type prod, great. If I type Bob, we will get must select environment, prod, dev, or UAT. Let's do the same thing for region. I have allowed regions, Canada Central, Canada East. Let me actually force a certain format here. We'll do it here as well. And this is going to be our default, but I'll accept more things just like we did in our last episode. Variable equals region, type equals string, validation equals condition, and error message. We'll say must set region to the same process here. Allowed regions, and for a condition we'll say contains local.allowed regions, but I'll replace value that is coming into region. So var.region is no spaces, doesn't have any spaces, and not only that, let's also put this in quotes and say lower. So lower the letters you provide in environment and then remove these spaces so that it always refers to this or this for region codes and allowed regions, regardless if you put capital letters, spaces, etc. And let's just double check actually and say environment prod, region Canada, space central, all uppercase, and it accepts it. Accept it as Canada Central without spaces, without uppercase. Let's keep going. And I want to dynamically create subnets later. So we'll make a variable for it. We'll say subnet underscore count and then type equals number. And then for our operators, we'll do validation, condition, come back to that, and they'll do an error message. Now, what do I want? Basically, I want count must be between 1 and 3. So the amount of subnets are either 1, 2, or 3, not more, not less. And the condition to make this happen is going to be var.subnet is greater than or equal to 1. And these are the operators we saw earlier, right? var.subnet count is less than or equal to 3. So if it's 1, it's 2, or it's 3, it will accept it. If it's not, it will not. And because it only accepts the type to be a number, if you type Bob, it will fail. So the types are part of your validation, not just the validation block. All right, now let's set up our locals some more. And we'll begin by setting up a map of common tag. Common underscore tag equals map. We'll say the first tag is called managed by equals Terraform. Always a good thing to add so that people know that this resource was made by Terraform and not users. Owner 1 equals my email and owner 2 equals my friend's email. And then we have cost center. And finally, let's do creation time. Because I want to timestamp when a resource is created. Format date, year, month, day, space, hour, minute, and I am formatting what? A timestamp of the current time. And next, let's dynamically set our virtual network's address space based on the selected environment. And we'll use something called Ternary operator, which we also looked at briefly in the last episode, which in Terraform are called conditional expressions. The syntax looks like this: condition, question mark, true value, colon, false value. You can think of it like an if statement. First part is the condition, which is tested for true or false bool. Question separates the condition from the first value, which is the true result, which it will set if the condition is true. And then after the colon is where it sets false value. Condition does not become true, it will lead to the false value being applied, giving us an equivalent of an if-else statement. And we can take it one step further and actually make if else statement, or if else if statement, where we do condition equals true, colon, condition equals true, colon, false value. It'll make a lot more sense when I show you an example. So let us write this conditional expression as a local. Address underscore space equals, and I'm going to use parentheses so I can make multiple lines. var.env equals to prod. That is true. We'll set the address space value that we are doing this operator on to 10.50.0.0/16, colon, meaning otherwise, var.env equals to dev, question mark. If it equals to dev, 10.60.0.0/16. Otherwise, var.env equals UAT, question mark, 10.70.0.0/16. Otherwise, or really I should say else, if none of the above, invalid. Make sure it's env, not end. So this effectively says if environment is set to prod, you're going to make it 10.50. Else if it's dev, you're going to make it 10.60. Else if it's UAT, you're going to make it 10.70. Else, as in none of the above, we're going to make it invalid. Now, you don't have to use this approach. I'm simply showing you what is possible. Earlier, I showed you locals being used inside a variable block. Now I'm showing the reverse, where a variable is being used inside a local. Let's look at another example. Maybe we have a storage account coming up. And it's the SA replication equals, same thing, var.env equals dev, or var.env equals UAT, question mark. If that is true, if it's either dev or UAT, we're going to set it to LRS. Otherwise, if var.env equals to prod, we're going to set it to GRS. Otherwise, else, it's invalid. Now, like we saw and before, the two ands right here, this is an or statement. So one or the other, we're going to set it to this as one part of our if statement. Otherwise, we're just going to do how we did earlier with the address spaces. It's prod, GRS. In reality, though, we'll never really reach invalid because we've already set allowed environments to be prod, dev, UAT, right? So if you're engineering this, why would you even include this when you're already hard coding what's allowed or not, right? So we could improve this. And how we're going to do that is, well, we can just remove the else. It's not necessary. You can have an if and else if, and that's good enough. But now if you think about it, one of them is GRS and everything else is LRS. Why don't we flip this? Why don't we say the environment equals to prod, make it GRS, else make it LRS. It's the exact same thing, just written a little bit more cleaner considering the validation limitations we already put in place with our allowed environment validation. Let me show you another approach, completely different from this. So instead of doing the ternary operator route, we could just make a map. So I can just say replication underscore type equals dev equals LRS, UAT equals LRS, prod equals GRS. And then we can just have another local called SA replication instead equals lookup local.replication underscore types, lowercase format. And what are we looking for? We're looking for var.env. So whatever is in var.env, whether it's dev, UAT, prod, it will set SA replication in that way as well. And now if we wanted to add more environments, we simply just add them here, and it's not going to be part of the calculations itself. Just trying to show you different ways. Like, we don't have to keep expanding, altering our conditional expressions themselves. We can just simply write them and use a function to handle the process. So far, we worked with simple values, things like strings, numbers, and boolean. We've also worked with collection, things like lists, maps, and objects. But those collections don't have to stop at this one level either. We can place collections inside other collections. For example, a map can contain another map, a list can contain an object, a map can contain a list, an object can contain lists, maps, or other objects all at the same time. A map can contain maps, that contains maps, that contains, you get the picture. And this is what allows us to model more complex infrastructure data. Instead of scattered related values across multiple locals, we can group them together. For example, an environment might have an address space, a replication type, a short name, or other environment-specific settings. Rather than creating separate maps for each setting, we can group them under one environment configuration. This makes the data easier to understand and reason, as they can all fall in line rather than calculating them all separately like we have just done with our environment. And it makes Terraform configuration easier to expand on later. Let's do one now and reduce some of our locals. And let's make a map of map. I'll leave the other ones here for now, but let's just say env_config equals map. Prod inside it equals map. Dev inside it equals map. And then UAT inside it also equals map. And inside each environment, we'll add key value pairs. We'll add both the network address and the storage replication type all in one go. So we can just say address equals, and we'll just use this one, 10.50.0.0/16. And then our replication can also just go here, and we can say GRS. Same here. Copy it over, paste it, 60, make it LRS. Copy this over, paste it, make it 7 LRS. So now we don't need this, and we don't need this, and we don't need this. And now we can reference these values based on the environment selected, prod, dev, UAT, and not need to calculate for address space or replication against our variables separately. Let's use an output to see how we can traverse map of map. So I'll just do an output here. Output equals, let's call it output. And then we do value equals, do a map, so I can show you two. So if you want to get the address space, for example, we can use lookup function, and then we provide local.env_config, and I'm looking inside it a particular key, which happens to be a var.env, right? So we prod. If I wanted to get to the address itself, right after lookup, I do a dot address like this. That's it. And then replication underscore type. I want to do the same thing, same process. I'll just copy this instead of address. You could actually use square brackets and say, in quotes, replication as in the key. And if I do Terraform plan, see how it looks. We'll say prod, region is Canada Central, the subnet count is 2, right? We got the values that are right here. And now whenever we're going to reference one of these, we can always just write this line into our resource blocks or whatever. But considering how it's getting along, probably a good idea to just make this into a variable. So now based on the environment set, we just reference one of these locals. It will do the calculation to get the value that we need. Now you may have noticed dot address and then the square brackets replication. Both work here. That's why I wrote it like this. It's up to you what you prefer. I prefer the dots, so I'm going to stick with the dots. And while we're here, since we have region codes, we should also just calculate them as well in the same fashion. So we can say region_short, because our resources will use them, and we'll do the exact same command, lookup local.region_codes, replace lower var.region. So we're making sure that the region values, whether they have spaces, uppercase, etc., accounted for and not erroring out, like that. This keeps our resources cleaner as a project grows. All recalculations are done in locals. That is what they're excellent for. Okay, we're done with locals for now. Variables are getting annoying to type. Just about time we start doing TFVARs. So let's make a file here. New file, terraform.tfvars. And in here, let's just put all of our variables, which is pretty easy to type because IntelliSense is here. Prod, region is Canada Central, subnet ID right here, and then subnet count 3. And now I can just run Terraform plan freely without all those pop-ups because they are all in here. Now here's an issue. I set my environment to prod, but the sub ID is not actually pointing to a prod subscription. If I go to my tenant, it is 1E something something, which is our development subscription. So like if I am working and I set it to prod, but I use my subscription to point to a dev subscription, that's a problem, right? Because deploying it to the wrong place. It's not something we want to do by accident. So if I go to corpo development and I go, well, any of my subscriptions, and I go to tag, I already have environment underscore short set to those environments that we set up in Terraform. It'd be nice if we could validate if the subscription ID we put matched our environment via those tags of the subscription. So for our Terraform, how can we actually compare our selected environment against the subscription? The subscriptions sit under provider, right? Well, you do that with the data block. So let's go down and type data, type Azure RM, and start typing subscription, and look, it shows up. And I'll just call it current, implying this is the current subscription we're going to be working with. And I'll say subscription ID equals var.subID. And with this, I can do an output. Value equals data, current, tags, and the tag I'm looking for is called env short. Let's hit plan and see what happens. And there it is. The tag is set to dev, which does not match our environment set to prod. If these are not matching, I do not want you to continue deploying anything in my Azure tenant. So how do we validate this? We're past the variable stage of our config by the time we run this data block, right? Set our variables, we set our locals, we're running data. Now what do we do? And let's explore more things, starting with check block. Check blocks allow us to validate our infrastructure. They evaluate a condition. Unlike variable validation, check blocks can inspect deployed resources, data sources, and other Terraform values. A check block contains one or more assertions. An assertion is simply a condition that Terraform evaluates. If the condition passes, the check succeeds. If the condition fails, Terraform reports a warning. Check blocks do not stop a deployment. They're designed to help verify assumptions, not enforce them. If you need Terraform to stop, preconditions and post-conditions are a better choice, which we will come to later. For now, let's explore check block. It is a block, so I'll type the word check. It shows up. And all it requires is a friendly name. I'll give it environment matches subscription. Sure. And then in here, you have the option type assert or data. I'm just doing assert here. And then in assert, we're typing a condition error message, just like we did in our validation. So the condition. So what are we checking if it's true? Is var.env. Let me just write the error message. Error message equals var.env equals data current tag env short. So we're testing if the environment variable matches what our subscriptions tags are. And if they do not, the selected environment does not match the subscriptions environment short tag. And if I run plan, this is it. We'll get a warning. It won't stop us, and it'll tell us what the issue is. Now, before we proceed, and I show you how we can actually stop this, let me actually show you another thing in Terraform. Like, what if I wanted this to be multiple lines? I can't do that. It starts erroring out. What can we do there? We can use Heredocs. Heredocs let us write multiple line strings. They're also commonly used by embedded code from other languages, party deployment, since code is naturally multi-line. For example, when you're creating a VM, we could use a Heredoc to embed a PowerShell or Bash script that Terraform passes to the resource. The syntax is as follows. EOF stands for end of file and simply marks where the multi-line string ends. One thing to note is starting with angle bracket, EOF preserves all indentation. If your text is indented in your Terraform file, those spaces become part of the string. So if you want to keep your Terraform code neatly indented without these spaces appearing in the final string, use angle bracket dash EOF. So let's do that. I'm going to remove all this, EOF, and then at the end, I'm going to write EOF. And in between here is my error message. So I can say the selected environment does not match subscriptions env short tag. And we can say selected environment var.env, selected subscription var.sub underscore ID, and then subscription tag. Let's just find the as data dot. Now if I run plan again, watch how the warning looks this time for our message. Right? So if you want to use multiple lines, if you're into that sort of thing, go for it. If not, you can make a single line. So now, even though the check failed, Terraform continued with the plan. Like, checks definitely have their place, but for this scenario, I want Terraform to fail. If my environment says prod and my subscription is actually dev, I don't want the deployment to continue. And fortunately, Terraform gives us a better option. Inside data and resource blocks, we can use called preconditions or postconditions. Pre and post conditions are built on the same validation concept we already learned. Just like variable validation and check blocks, they have a condition and an error message. The difference is where they're used. Instead of validating variables, they validate resources and data sources as Terraform runs. Both live inside a lifecycle block. The lifecycle block is what's referred to as a Terraform meta argument. We'll unpack meta arguments shortly. For now, let's focus on these conditions. A precondition runs before Terraform creates or modifies a resource. It allows us to verify that our requirements are met before Terraform continues. If the condition value is false, Terraform stops with an error. A postcondition runs after Terraform has created a resource or read a data source. It verifies the result is what is expected. If the condition value is false, Terraform also stops with an error. These become useful whenever your Terraform configuration depends on assumptions that variables alone can't validate, such as checking a subscription tag, confirming a resource property, or validating information returned from a data source, etc. Okay, so let's do that. I'll keep the check block for now, but let's go into our data block and let's add lifecycle. I type L, it shows up. And inside this block, we'll create one of these conditions. In our scenario, we first need Terraform to read our subscription. Once the data has been read, we can inspect its tag. Then we can compare the subscription's environment short tag against the value supplied by our environment variable. Since we're validating the result of reading a data source, we'll use a post condition because we want it after it has been read. So we'll simply take the condition from our check block and move it into the post condition. I'll copy everything within assertion. And here I will type post condition, and in this block I'll just paste it. And we're good. And then I can remove the check. Now there's one thing we do need to change. Like, I'm inside a data block and I'm referring the data block within itself. You don't do that. What you refer to is something called self. Self refers to the current resource or data block. Anything after self is simply one of the object's attributes. So all this can be replaced by the word self, and then the same here. So now let's run Terraform plan and see what happens. Plan is going. It reads the resource block for the data, and now it does a terminate. We cannot proceed with apply like we did here, where you were able to run Terraform apply. Perfect. Right now, our environment variables don't match the subscription we've selected. That's exactly the kind of mistake we want Terraform to catch. I'll show you an example of precondition later as well. Before we continue, let's talk about this lifecycle block, which is a meta argument. Meta arguments are special arguments in Terraform that control how Terraform behaves. Unlike arguments such as name, location, or skew, they don't configure the resource itself. Instead, they control how Terraform creates, updates, and manages that resource. We just explored one of them called Lifecycle. It gives us more control over how Terraform manages resource through its lifecycle. Inside Lifecycle block, we have features such as precondition, postcondition to validate our deployments. Lifecycle also has other arguments that you could use, like prevent destroy, to protect resources from accidental deletion through Terraform destroy commandlet. And then there's ignore changes, to tell Terraform to ignore attribute changes of a resource, even if they're done in the portal. And there are other meta arguments as well. In the last episode, we actually explored one of them called depends on, which lets us explicitly control the order Terraform creates resources when dependencies aren't automatically detected. And other common meta arguments include count, which creates multiple instances of the same resource using a number, for each, which creates the resources by looping through a collection such as a map or a set, provider, which lets us choose which provider configuration / alias a resource should use. We'll explore many of these throughout the rest of the episode. Let's move on to our first resource block and actually start creating some infrastructure. And we'll begin with resource group. And I'll use IntelliSense to scaffold the resource. For the name, let's use some of the functions we explored earlier. We'll use format with %s placeholders and reference both our variables and our local. Format rg-%s %s001, comma, var.env for the first one, and then local.region short for the second one. And for our location, it will be var.region. Next, let's add our tags. Well, let me throw in a small curveball. Our common tags already exist in locals, right here. But what if this resource also needs additional tags that are not there? Now, rather than recreating the whole tags map again, we could actually merge the common tags from our locals with our own data using a merge function. And as the name implies, it combines multiple maps into a single map. So you type merge and you put parentheses. And inside the parentheses, we'll pass in our common tags first. Let's hit new line so we have multiple lines to work with. And I'll type local.common tags, comma. And as I said, this uses maps. So inside the merge, we're actually going to make a map by using curly braces. And now we can add the names of the tags that we want to use as well as their values. So I'll say project name equals Terraform 102. And then let's say application equals core in whatever, right? And let's do a Terraform plan. I'm still getting that post condition error. So let me just address that. And we'll make an environment dev because everything else is already pointing to it. And let's do plan again. Perfect. Our tags will be known after apply. So let's apply. Terraform apply. Cool. Now I want to see what the tag values actually are. And I don't want to hit Terraform plan again just to see that value. So we could use a command called Terraform Show, which I showcased in the last episode. It is a great command to display the context of our state file in a human readable format, aka the HCL language. It's also great if you wanted to reference an object key but don't know the name. What I mean by that is by type Terraform Show, there are all the tags. But if there was a value of a resource that I didn't set, but I want to extract it for use for later, well, they will show up here about the resource as well. Like for our subscription, there's so much more data about it that's showing up here now, right? So if you need to know what attributes are available for a data block or a resource block, you can use Terraform Show to kind of get that information, and then you can build your next piece using that information. Now let's look at creation time. And I added that tag the way it is for a reason. The intention for it is to represent the time that the resource was first created. So if I run Terraform plan again, notice Terraform wants to update the tag. It looks like it's deleting all because that's just how merge works, but it's actually just altering one, but it's recreating the whole field. And that's because timestamp, which is in our local here, is about the current time. Every time this runs and these tags are being applied, it's adding a new date time to this tag, which kind of defeats the point of what creation time is. So if I apply it now, it will set a new time. If I apply it later, it will set another time. And on and on and on every single time. Now, I don't want that. I just want it once it's created, that's the time we set. And after that, I want to ignore this tag. So let's fix that with another lifecycle option that I mentioned earlier called ignore changes. So in our resource group, let's type the word lifecycle, and then let's type I for ignore changes and hit that. And this looks for a set, a list of items. So inside this list, we want to specify which arguments Terraform should ignore. Now, I particularly want to ignore tags, but not all of them. So what I'm going to do is I'm going to put in square brackets the name of the tag that we want to ignore. So creation time, just like that. So from this point on, Terraform ignore changes for this particular tag, but any changes to any other tag will still affect it. Now I'm going to take this one step further. I have automations that populate creator and creator type, but they're only for resources, not resource groups. So you're not going to see them yet. I don't want Terraform trying to overwrite them when I copy these tags over, so I'll just add them now so that I can just paste this lifecycle ignore changes for all my resources going forward. Why don't we just make this into multi-line, so just a bit more clear. And I'll do tags, creator, tags, creation type. So now it's going to ignore all three of these tags with these particular keys. And I'm not just limited to tags with ignore changes. It can be any field that can be altered with a resource. Let's move on. Now let's add a virtual network, and we'll point out address spaces to the local we set based on our environment right here. And we'll include our tags and lifecycle block here as well. So resource, Azure RM, network, vnet, name equals vnet dot dash, let's do string interpolation this time, var.env, local.region short 001. Location, var.region, group.name, space, local.address space, tag. Now I want to show something else about tag. We'll just copy this is going to be the same. And maybe I don't care about these. Now, what if I have a cost center that is going to be different for our virtual network? Maybe it's a different team that manages virtual networks and they have their own cost center, right? But in our common tags, we already wrote one. Is it possible for us to overwrite that? Yes. Merge works from left to right. So if the same key exists more than once, the value on the right will win. Like this is technically one line, right? Local common tags, comma. So this is first thing, and then this is the second thing, as in what's to the right or bottom, depending on how you format it. So we'll say cost center equals 4001 instead of 1001. And I'll ignore these lifecycle changes again and do Terraform plan. And I'll show you creator and creator type, creation type. Cool. But if I look for this VNet, go to tags, we have creator and creator type. That is done by my automation that automatically adds who it is that creates resources in my tenant. So SPIT Terraform, our app registration, and the type is an app registration, aka application. And now you can see the cost center is actually 4001 and not 1001. So our merge has overwritten our previous value. Now let's create our subnets. In fact, I want 3 subnets in this VNet. And let's just remove this output. So let's create one. Resource, Azure RM, subnet. And we'll call it subnet. I'll give it a name. First, let's add our address prefixes. Could hard code a subnet from our VNet address space, so we can say address space equals, well, this is dev, so it's going to be 10.60.0016, right? So I can write a subnet space in it like this, right? But now, since we had our little fun with CIDR functions earlier, let's use that instead. Instead of writing this, I will write CIDR subnet local.address space. So it'll be the same address space that is being used here, comma 8, comma 0. So give me /24 in the first position. And if I run Terraform plan, okay, I should this creator type. If I run plan, there it is, our address space for the subnet, /24. Now, if I wanted 2 more subnets, the obvious approach is obviously to copy this block and change the name and the address prefix. So we can do that. Call this 002, and then we can call this 1. And then if we want to do another one, and then make sure you change the friendly name too, so we should call this subnet B. And then let's create one more, subnet C, call it 3, and then call this 2. And if I run plan just to see how it looks, it should fill out 3 different spaces for us. So for subnet B, we have 60.1. For subnet C, we have 60.2. Great. Now imagine if you had to do 20 of these. Do we really want identical subnets blocks like this? I don't. So let's look at what's actually changing between these. The first subnet uses a numeric prefix 001 and then a 0. Second one uses 002 and then it's a 1 for the position. And then 003 is 2 for the position. The pattern is obvious. The only things that are changing between these are numbers, which means it is a perfect time for us to introduce loops. Now, loops allow Terraform to repeat work for us. Instead of writing the same resource block over and over, we can write it once and let Terraform generate the rest. Terraform provides two primary looping mechanisms, count and for each. Both create multiple instances of a resource. The difference is how they decide what to create. Count works with numbers. It simply repeats the resource a specified number of times. If count equals 3, Terraform creates 3 instances of the resource. Each instance receives a numeric index starting at 0 and counting upward. Count is best when your resource is almost identical and only a number separates them. And we're not just limited to using numbers, but also lists, as they're technically indexed by numbers too. For each works with collections, such as maps. So instead of counting from 0, Terraform loops through each item in the collection by using their keys. This makes for each ideal when each resource has its own unique configuration within the map. So let's explore these next, starting with count. Let's comment out the additional manual blocks that we've written for subnets, and let's just convert this one. And the first thing we're going to do is in our resource block, let's call this subnets. And before anything, it's always a good habit. You're going to do a loop to put the looping mechanism at the top of the resource. If you write this attribute, it'll be very easy for anyone skimming through your code to know that this is a loop, rather than putting it somewhere in the middle and kind of obfuscating it. So we'll say count equals 3. So we're going to make 3 subnets. Now this is enough to make 3 subnet creation attempts. The problem right now is it will still try to make the same 3 subnet names with the same address prefix with the same position. So in other words, it won't work. And for the name, I want to show that you don't actually have to use string interpolation or format. You can actually combine both. Where we previously have 001, I'll write in the string interpolation format. And in here, we'll use our %03d, like that. Keep the same 3-digit naming style. To reference the current index, so the first loop, the second loop, third loop, what you do is, rather than writing a number, we'll do count.index plus 1. Remember, indexes start at 0, and for our resource names, we want to start with 001. Hence why we're using arithmetic. Add 1 the way we are. Leads us to our next conversation. Terraform can perform arithmetic with numbers. Rather than hard coding each value, we can calculate them dynamically using math. We can sometimes use it to calculate values, other times to just like we just did with the index. Next, we want to update the address prefix. So this 0, like I said, is going to be changed every time. We're also going to say count.index here. And the reason why we're not doing +1 is because we want the first position, which is 0. For our next loop, we want position 1. And for our next loop, we want position 2. And that is all we need to do to make the 3 subnets without 3 resource blocks. Let's run Terraform plan and see this in action. There you go. Our first subnet, our second subnet, and third subnet. And then each subnet name, as you can see here, has the index mentioned. This is 0, this is 1, this is 2. The name is 001, 002, 003 because we did the +1. And then our subnets are matching our index numbers. There's no overlap, there's no collision. Pretty cool because I can create as many subnets as I want, essentially, by adjusting this number. So if I wanted 10, we can just do that kind of thing, right? Or if I wanted 12, I could do that. Let's just stick to 3. Let's remove these lines and hit Terraform apply. And here's a great example of creating 3 things at the same time. Like just because it's looping, it's not going to create one, then create the next, then create the next. Now, I don't want my subnet names to be this cryptic. Like, I don't want them to be called subnet dev cc003 and 2 and 1. In a real environment, you want to give them more of a name that represents what those subnets are for. So let's switch from using count to using list. I'm going to go to my locals and I'm just going to add one more line here. And we'll call it subnets equals list. First one could be general. Second one could be called MySQL. Third one could be called app services. And as I mentioned before, lists are accessed by indexes. That makes lists fit perfectly with count. because count also works with indexes. Let's alter our subnets resources to use this list now. Let me just go to Terraform Console and let me show you another function so we don't have to test with plan. If I do length equals local.subnets, it returns the number of items in a collection. Since our list has 3 items, length will return 3, which fits right here because if we want 3 from a list, we can say length local.subnet. Now for the name, instead of writing 001 like this, I wanted to write general, MySQL, and app services. And we can do that using list indexes. So if I go to Terraform Console again, and I type local.subnet 0 like that, local.subnets with an S, do 0, I'll get general. And then if I do 1, I'll get the next one, and so on. Here, we can do that. Instead of writing this, we can do local.subnets. And instead of writing 0 or whatever, we can do count.index, because the first one was 0, the 1, and 2. The address prefix will stay the same because count.index still works. Let's run Terraform plan and see what happens. Now, Terraform is going to replace the existing subnet. That's because we're changing the name, right? 003 to app services, 002 to MySQL, 001 to general. So let's run Terraform apply. Now, the nice thing is, if you ever wanted to add more to our subnets, all we do is add to our list, right? If I wanted to have a subnet called private, I can just write that, and that will be the 4th subnet in our collection. Okay, create. Now, if I do Terraform plan, it will add our 4th subnet. Terraform takes the next available index, being 3 because it starts with 0, and creates the next subnet for us called private. Great, right? Let's not do this. Let me actually show you something else. So let's pretend in our VNet, these subnets are now being used. General is being used, MySQL is being used, app services is being used. And then our org decided that we don't need this subnet for MySQL, but we want to keep the other 2. Okay, fine. If we can add subnets, we can remove subnets, right? Let's do that. Let's just remove MySQL from the subnets and keep the rest and run Terraform plan. Wait a minute. What? It's destroying app services and it's replacing MySQL with app service. Why is it destroying 2 subnets? It's supposed to be destroying MySQL only, but it's also recreating app service in position 1 on the index. And that happens because of how count works. App service used to be the 3rd one, so 0, 1, 2. And because we removed MySQL, which was in position 1, app service moved to position 1. And because Terraform now sees app service as index 1 instead of index 2, it also changes app services subnet. It no longer gets 0.2, it actually gets 0.1 that would be for subnets. So from Terraform's perspective, that resource changed. So it wants to recreate it. This becomes a real problem with count once resources are already using that subnet, right? Removing the last item in the subnet list is fine, but removing something from the middle or adding something at the front is going to cause all these kind of alterations and move index around and put them in different subnets and delete them. So what can we do to avoid that? We needed a loop that identifies resources by stable names instead of numeric indexes. And that's where for each comes in. For each is based on keys. It works much better when each item has its own identity. Let's transform this to use for each. First, let's replace our list with a nested map. I want to add more settings to each subnets later anyway, so a map gives us more room to grow than a list like this would have. For now, we'll just hardcode the positions inside the map. So we'll say subnets equals map, general equals map, so we're doing nested. Subnet underscore position equals 0, which would be 10.60.0.0.15. SQL will be subnet position, I should write equals here, equals 1, this, and then finally our app service. Now let's head back to our subnet resource and alter this as well. By the way, if you ever need a quick way to move around, especially when your list gets long, called outline right here in VS Code. And as you can see, all of our blocks are written here, right? And if you want to collapse them all, I think So if I wanted to go to my provider block, I can just click this. If I wanted to go to my subnet, I'll just click this. Makes it a little faster, and let's just do that for now. Okay, so our subnets will point for each to our map. We'll replace count with for each equals local.subnet. Now each item inside the for each is referenced using each. The keys are the names we want to use. We can reference those with each.key. So we can actually replace this and say each.key, which if I should go back to locals is general, MySQL, app service. The map values are objects stored under each key. And then each value for them is each.value. But since each value contains another map called subnet position, we can actually reference it like this for here. So we can do each.value.subnet position. And that should do it. Yep. Do Terraform plan. And because we changed how our resources addressed, Terraform will recreate our subnets once again. But this is the way we want it to be, so that's great. So just to show you, it's not overwriting the original ones because they had a completely different format, right? Each thing is indexed by a number. Now everything is indexed by their keys. So deleting all the index numbers and it's replacing them with these keys. And then you can see here, it's not the order that we had in the keys, but you can see app service is 02, general, which is the first position, is 0, and MySQL is 1. So let's do Terraform apply. And then once these are created, we'll remove MySQL and see it only delete that. That's fine. Well, I'm deleting them, recreating them with the same names and everything, so you can see why that'd be a problem, but it's fine. I think if I run plan and apply again, it should overwrite it. So our resources are created. Clear this. And now we can just comment a line out. If you run Terraform plan, it should delete only that subnet and keep general and app service. Perfect. Only one thing is being deleted, the subnet for MySQL. The rest stay exactly where they are. That's one of the main benefits of for each, where each resource we deploy through it is safe because of the key. I'm just going to uncomment MySQL and keep it for our next step, because the beauty of using for each is not just the fact that we have different resources being looped, but we can actually create multiple settings for them that are unique to each of them. Like for example, MySQL and app service. The reason why they're called a resource name is because I'm going to make them delegated subnets for those particular resources for private access through the VNet. And general can remain the same for regular subnets for everything else. Let's go to the Azure subnet settings in the portal and look at the names for delegation. If I have my subnets, and I was going to do this manually on the portal, I'll click MySQL or app service, and I'll scroll down. And then notice something here too. Private subnet is checked off by default. Maybe for MySQL or something, I want to turn it on. We'll look at that later. But the key here is subnet delegation. You have all these particular resources that you can lock this server to. So for MySQL, it's actually called flexible. Yeah, right here. MyDB for MySQL flexible server. I have this name copied on my other screen, so that's fine. And then for app service, it's like an older name called server farms. That will be for the app service. Cool. I'm not going to do it here because we're managing through Terraform. We'll do it here instead. For MySQL, I will say delegation, and it will be that. And then delegation for our app service was server farm. Let's just run Terraform format and get it all sorted. Cool. So regarding this setting, enable private subnet. Let's go to the doc for subnet and look for it. Enable default outbound access, defaulting to true. So you are able to go outbound, aka it's not private. And this expects a true or a false. Again, the key thing to highlight is the defaults to true. And as I said, I only want to set it to my SQL one. So I'll just do it here. And let's just give it the same name to just make it clear. Like these are just variable names, right? So I can call them anything. I'll just use the same name just for clarity's sake. Now this gives us a useful problem to solve. Some of my subnet objects are this. Some have 3 things, some have 2 things. When a value isn't provided, I want Terraform to behave as if it was never set. So when this is not set, its defaults are true. I don't want to set it to true when it's not there. I want to set it as if it never was used. This is where null, which is another data type, becomes useful. Null does not mean empty string. It does not mean false. It means treat this attribute that I've set to null as if I never set it to begin with. So whatever the argument's default was, that's what it's going to set, whether it's true, false, some words not used, etc., etc. And Terraform will just fall back to its default behavior as if it never existed. So I want this field, default outbound enabled, in my subnet. Called the default outbound access. Now, how do I programmatically set this so that it only tries to set the value if it exists for one of the keys in the map, but it nulls for everything else? We have a try function where it evaluates an argument expression, and if it doesn't find it, rather than failing, before I do that, if I wrote this, each value default blah blah blah, this would fail because two of them don't have it. But if I use try, rather than failing it, we can have it do a separate assignment. So try to set this. If it doesn't happen, I want you to set the value to null, aka do the default. So in plain English, try to read a variable called default outbound access enabled in our map for our subnets. If it exists, use that value. If it doesn't exist, return null. Like technically, I could hardcode true here or any field because the default here is setting to true, right? But I want it to behave as it would normally. So I'm setting it to null. Because null is a better way to say, do whatever the provider would normally do by default. And if I do Terraform plan now, you should only see one of the subnets being modified because that's the only field where we're actually making a change. Just like that. So my subnet for MySQL, this is being set from true to false. App service and the other one are not being touched. And I did have two more, right? The delegations. Let's work on them next. A delegation is different from default outbound access. It actually shows up in the example here, where default outbound access enabled is an attribute where you write a value. Delegation is actually a block. It's a nested block within our resource. So if we were to hard code what I'm about to show you, for example, let me just write in plain text what we're going to do here. So delegation name equals delegation. Service delegation is name equals our delegation name. And then the actions, something that's pulled from the internet. And then there's this action to join the subnet to the VNet. Whatever. Now I want this block to be dynamic just like we have here. So if the subnet has a delegation, create the delegation block, like create this for our app service. Because delegation is a nested block, we can't handle the same way as we did with the argument. This is where dynamic blocks come in. Now, dynamic blocks allow Terraform to generate nested blocks automatically. Rather than writing the same nested block multiple times, Terraform can create them for us based on our data. They're similar to for each, but instead of creating multiple resources, they create multiple blocks inside a resource. This makes them ideal when a nested block is optional, repeated, or varies between resources. For example, a subnet may or may not have a delegation. A network security group may have security rules, many of them. Rather than manually adding and removing nested blocks, we can let Terraform decide when to generate them. Dynamic blocks are simply another way to programmatically build Terraform configuration based on the data we provided. Let me show you an example with delegation to use it conditionally. Later on, we'll build an example of adding multiple nested blocks via a loop. So inside our resource block, let's just comment this out for our reference, and let's make this dynamic block. The argument is dynamic, so you type dynamic, hit enter, and it'll create the block for us. I'll just call it delegation. Now, even though we're just checking whether it exists or not, we kind of have to use for each with dynamic block, but we can actually make it into an if statement. So bear with me. For each equals lookup, and this is kind of like try, where rather than looking up a value, we're looking up a key and its resources. Look up each dot value for a key called delegation. So in our map for our subnets, if I am in MySQL or if I'm in app service, look through the keys for delegation in there because it's a map of maps, right? And then if it doesn't find it, write null. So far, just like our try. But after that, we're going to do one more step. Now, just because we set it to null in for each doesn't really do enough. So what we need to do after this, look up is our ternary operator, our conditional expression. We're going to say whatever we got from here, if it does not, because that's what this means, equal to null, we're going to make for each into 1, meaning you're going to loop once. Otherwise, you're not going to loop at all because it's nothing. So this will either loop once or none at all, effectively making it an if statement based on whether we had a delegation key or not. A pretty advanced way to do this, but I thought it'd be a cool way to show you. Technically, dynamics are to add multiple items by writing all of this. This is just a trick you can use to make it more of a conditional statement. Kind of a wild way to make something work, but hey, welcome to Terraform. Now, because it exists, we can just reference our context block inside our setting for the setting as if you were adding this information to the delegation block. So the next thing we add is content, name equals delegation, right? So now we're actually doing this part. And then we have service delegation, name equals, well, this is going to depend on what the value is in delegation, right? That we're pulling from here. And then actions, well, I'm just going to do this particular one. So let's just write that here. And that's it. We use the dynamic block to make a little if statement, and if it's true, we add our nested block inside our subnet. And let's run plan, and we should get an update for our MySQL, and we should get an update for our app service. Cool. So our subnet for MySQL, setting up our private subnet, but it's also setting up our delegation for MySQL server. And then if I scroll up for our app service, the only thing it's doing is setting up our delegation for server farms, effectively making them subnets only for those resources. And let's just hit Terraform apply. Okay, done. And if I go to our subnets and I hit refresh, you can see delegated to is already set. And if I click MySQL, this is checked on, but if I click something else, it is not checked on, but our delegation is set. Perfect. That dynamic block if statement was a bit of a mouthful. So let's look at a simpler way to conditionally create another resource. Let's say you want an NSG in our production environment only. We can actually use count for this as well. Like earlier we saw count equals 3 to create 3 resources. Count equals 1, create 1 resources. What do you think count equals 0 does? It creates nothing. And so we can use that effectively to turn count into an if statement as well. So let's just write a quick little NSG here. I'll say resource, Azure RM, network security group. And we'll call it NSG. Name will be the same as our other format. Environment region short. Location, var.region, and then resource group name, Azure RM, resource group rg.name. And let's just use common tags. And let's use our lifecycle. Terraform FMT. Okay, so to make this an if statement using 1 or 0, we're just going to write count equals, well, I want it to be a conditional expression, right? So if the environment is prod, I want to set the count to 1. If the environment is not prod, I want to set it to 0. So var.env is equal to prod. If this is true, 1 is what we're going to set. Otherwise, 0. In other words, if the if condition is true, create 1 NSG. Otherwise, don't create 1 at all. You can see if statements are kind of cryptic in Terraform. There's no if statement. You kind of have to like build them in some way. Either you create it like this, or you create it like this, or create it like this. Right? It's one of the confusing part about Terraform, but once you get used to it, it's pretty straightforward. Now let me just run Terraform plan and let's see what happens. I'm not in var env for prod, so this should not do anything. Yeah, some delegations require other things. Let's just ignore them. That's not the point of my course right now. So let's just say lifecycle, ignore changes. And what do I want to ignore? I want to ignore delegation. So the field that is delegation, all of this, any changes that occur into it, just ignore it. Just like we did tags earlier. Now let's hit plan because we're focused here right now. No changes. Your infrastructure matches the configuration. Wonderful. And that's because our environment is set to dev. Now, if I change this to prod, it will create it. Now, if I have to do that, it's going to recreate every resource. I don't think we want to sit through and wait for that. So let me just change this to dev, and let's just pretend it's prod. So now, because it's looking for environment dev to create an NSG, if I hit plan now, there you go. Now it's creating it. And you can see the name is network NSG 0, first item in the index, right? And it's going to create it. Now let's build on the NSG. Right now, the NSG exists, but it isn't associated with anything. Maybe we want to associate it with our general subnet. Let's do that next. First, let's create the association resource. Again, I'm not going through how to find the resources and use them. That was the point of the last video. Today, we're just working on the programming cell. The resource, Azure RM subnet, network security group association. We'll call it subnet NSG association. And what does it require? Probably the reference of subnet and NSG. Yeah, okay. Subnet ID and then network security group ID. We'll come back to both of these, but let's talk about something. Now, because this is created via count, this is also going to be created via count. Like, you don't want to create this if this doesn't exist. So you should do is count equals var.env equals dev question mark 1 question 0 Terraform format. Now we need the subnet ID. Remember, our subnets were created with a for each. That means we're referenced by keys. So Azure RM, if I do Terraform Show, and let's find our subnet real quick. Right, so this is one subnet. This is another subnet. This is what we want. We're going to reference it by its key. We'll do Azure RM, subnets like that, square brackets, quotes, general, dot ID. Like that. Next, we need the NSG ID, this resource. And this is going to be a little tricky too. So Azure RM, NSG. This is not enough because we set it to have a count, right? If I look for the NSG somewhere, but this is going to be the name, NSG with a 0. So you need to make sure that you indicate that. So if you use an if statement using count, the resource is going to be referenced with a 0 always. And now if you run Terraform plan, it should associate with all the resources as we intend to. Our NSG is going to be created, and then our association to that NSG will be created. For each, referenced by keys, count, referenced by indexes. Now let's explore a more common use case for dynamic blocks for our NSG. This time we're not going to use it like an if statement, but rather loop through a map to create our dynamic block. Let's look at the NSG documentation. Security rule. Security rule is a list of security rule objects representing security rules. I could just make it into separate resources too, but let's just use dynamic blocks as we're trying to learn dynamic blocks. Idea with the NSG is you don't just create one rule, you can create n number of them, right? Some allow inbound, some allow outbound, some deny, some deny. So this block will be repeated over and over and over and over. This means we can add multiple security root blocks inside our NSG. So let me just show you how you would write them manually first, and I'm just gonna paste it. There's too much to pretend to type. Terraform T. So you can have a rule like this, you can have a rule like this, and a rule like this, and a rule like that, etc., etc. All fictitious stuff. Just want to highlight that it's a lot of repeated code. Now imagine 20 rules, 30 rules, or the same pattern across multiple NSGs, right? One for general, one for MySQL, one for this, one for that, blah, blah, blah. But now let's look at a pattern here. Notice how many values are repeated. So many of them have asterisk, right? Asterisk, 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 asterisk. And potentially not. We can clean that up. And then a lot of them are just repeated, like allow, inbound, outbound, etc., etc. What can we do? Well, we can make a more unique rule data into our local, as in nothing that gets repeated. And I'll paste this in our locals for the interest of time. And this time, instead of a map of maps, I'm doing a list of maps. And remember what could happen with lists, right? You remove something. Now here are the rules, and I added a few more. Notice I didn't mention anything that has an asterisk. And notice I didn't mention the protocol TCP anywhere, except for when it was a value for UDP for these two. Also notice I only mentioned denies. So access deny is the only time I've mentioned it. For the rest, I did not. So I'm going to use defaults later. And then in our NSG, let's use dynamic blocks instead. dynamic security rule. We'll do for each equals local dot network security rules. This dynamic block will now loop through each item in that list. Next, let's add our content. And this is the block Terraform would generate each time. So all the name, priority, direction, etc., is what we do here. So name equals security underscore rule dot value dot name. This is what the friendly name is for, right? Priority, and then let's just do two more of them, priority and direction, because these are fields that in my locals I will always have. Name, direction, priority always exists. Now let's handle values where we want defaults. For access and protocol, meaning allow, deny, or TCP, UDP, I want defaults if they aren't provided. So access equals security rule value, blah, 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 dot, comma. So we'll do lookup that we did earlier, right? And we'll do the same value and say if there is a value for access, use it. Otherwise, set it to allow. And then this one is protocol. There's a value for protocol, use it. Otherwise, set it to TCP. And we'll do the same for the remaining fields. So source, we'll do a lookup. If it doesn't exist, asterisk. Actually, destination port is something I've set to required. So set that value as is. And then the other two will do the same, where we'll say the value exists, use it. If it doesn't exist, set it to asterisk. That's it. Made our dynamic content to be able to read from our locals. So Terraform plan. Let's see what happens. Hopefully I typed everything right. And just like that, they're all being created. Perfect. So I can do Terraform apply now, and then we can actually see it in the portal. Go to our NSG. And there are our inbound and outbound rules to let connections in or deny connections. Perfect. Now what happens if I decide, oh, I don't want this one anymore, and I run Terraform plan? It's going to delete all of them? It is a list, right? Yep, it's going to remove all the ones after it and then recreate it. So the same count little thing applies because we're using indexes and not mapped. But like it's NSG, so who cares? It's going to remove and apply them anyway. Either way, just like that, Terraform is generating our security rules. We saved a lot of repeated lines, especially if we plan to make multiple NSGs. So if we had multiple of these NSGs being created, right, we can just reference this one dynamic rule from our local or our variables to do so. Next, let's look at another kind of loop. This time, we won't use a loop to create resource or blocks. We'll use a resource to transform data. And that's where for expressions come in. For expressions allow us to loop over collections and transform data into a new shape. Unlike count or for each and dynamic blocks, they do not create resources or nested blocks. Instead, they return new values. You can use them to extract specific values from a collection, rearrange data into a different structure, filter items based on conditions, calculate new values from existing data. They work with collections such as lists, maps, and objects. Think of them as a way to say, for each item in this collection, build me something new. Let's explore the for expression using outputs. So I'm going to create an output here, and I'm going to call it NSG rule name. And all I want is the names of our NSG rules. So all these names. But what we could do is inside a list, because we want a list, we'll say for rule for X in Y. So for rule in local dot network security rules, give me rule, which is the variable we basically created, dot name. So if I do Terraform plan, all right, don't do local, just local. If I do Terraform plan, we got our list of all of our rules. Not that exciting right now, but let's make it more interesting. So instead of returning a list, let's reorganize this data. We'll group the rules by their direction, inbound, outbound. So what we could say here is instead of it being a list, let's make it into a map. And we'll stick to the for as is. So we use rule as our variable. Make a new line here and say rule underscore dot direction. I want you to set this as the key And inside the key, whatever rules match this direction, I want them to be set as the value. Be a lot more clear when I hit plan. Oh, and make sure you do ... Right? So now we just made our own map out of it, which is all the rules that are inbound and all the rules that are outbound. These are how they're categorized. A little bit more useful. Let's keep building on it. Like, rather than showing our rule names, let's also include their destination ports as well. So we can use string interpolation for that. Right here, let's just do quotes. Put this like so. How do I want to write it? After the name, I want to put a space. And then I want it to be in parentheses, the rule. So we'll do another string interpolation and do destination port range. If I do plan, right, there you go. But because we can also use them to make values, like you can use this in your for each too. So like if you only wanted to apply all the inbound rules in the NSG and not the outbound, like you could run it here as well, kind of thing, and only target them if you wanted to. As you can see, for expressions are excellent at reshaping data into whatever format you need. For example, before creating an NSG, I might want to verify that every rule priority falls within Azure supported range. Let's say that range is 100 to 4096. You can do that by combining it with a precondition. Add this to the lifecycle of our NSG. Right here, we can do a precondition and say condition equals all true. So if all of these things are true, great. Otherwise, we're going to have an error. I'll come back to this. Let's just write error message so we can get rid of this. And say all NSG rule priorities must be between 100 and 112. And then what do we do in our condition? Well, we can do a for loop. For rule in local.network security. I'll just do it in a new line again. Rule.priority is greater than 100 and rule.priority is less than or equal to 4096. So here the for expression evaluates every rule before it even tries to create the NSG. And if the result is a true, fine. If the result is a false, it will fail the job and error out. Let's prove it. Let's go to our locals and let's make this one 5000 and do Terraform plan. Perfect. Expected security rule priority to be blah, 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 blah. We gave it a big number. So if I undo that, do Terraform plan, it works. And I want to show that example just to indicate that for expressions aren't just for outputs or anything like that. They can also be used as calculations for whatever computation that you want to do. It's just a way of manipulating data and then using that manipulated data to collect some kind of information to do certain kinds of things. And while we're on the subject of expressions, let's look at another newer expression called Splat, which behaves similar to for. I'll call this rules by direction, so it doesn't affect this. And let's paste this old one that we had earlier. And this works just to give us the name, right? Like pretty straightforward. And if I run plan, let me just show you, like it's just giving us the list of all of our NSG rule names. And because all we're doing is just collecting one field, there is an easier way to do that too, using a Splat expression. And it's so much easier to type that if this is the case, you can just do this. Local.network security rules. Rather than providing a particular name, you do asterisk to say Splat and say .name. So get me all the NSG rules that exist and get me just their name. So if I run plan, asterisk will iterate through every item in the collection, and then the .name will return just a name field, looking exactly like how it did before. So a Splat expression is really just a short way of writing this kind of for expression that we saw earlier. I personally don't use Splat expressions very often unless it's simple queries like that. I tend to just reach for the for expression instead because they're much more flexible. Let's head back to our variables and start building some rich data types. So far, a lot of our configuration has been hard-coded in locals that kept things simple when we were learning. But in real Terraform projects, many of these values need to come from variables instead. Variables are not limited to just primitive types like string, number, and bool. We can also create variables with much more complex types. Let's start with a simple list. I'll just put it here in our locals for now. And this is what I want to convert into a variable instead. In order to do that, you type variable, container types, we'll give it the same name. And then for type, rather than string, whatever, we'll type list. And as you type it, you'll see square brackets. And then in there, you'll have the option of putting a different type. So because this is just a list of strings, we'll type string. And if we want to, we can keep nesting more complex types in our types. But for this example, list is enough. Now, if I ever do default in something that's a number, it gives you a number, right? And if I do default in a string, it gives you a string value, right? If you try to do default here, IntelliSense will actually put it in a list and say, give us a list of values. Pretty cool. But in today's episode, we're not really going to work with containers. I'm just going to remove these lines. We don't care. And let's look at some more advanced examples. And we'll look at our subnet that we have here. I don't want this as a local. I want this to be something that from the outside somebody provides, right? So that's what we're going to do, where they choose a subnet name, they choose positions or whatever else they want to set, the delegations, etc. I may have more fields that we enter in the future kind of thing, right? I want this to be a variable that accepts the structure. And I'm going to actually limit it so it can only accept position, delegation, and default outbound access enabled. In my last episode, I mentioned that an object versus a map. An object just means a predefined attribute, where a map is more open-ended, where you can set the keys, not just the value. So what we want here is technically an object. Well, it's going to be a map, which is going to have n number of keys. And then inside those maps are going to be objects, which are going to have these particular attributes. Because I may have a MySQL subnet, I may not. I may have an app service, I may not. But I'm going to have, if you make one, a subnet position. I'm going to optionally have delegation, and I'm going to optionally have default outbound access enabled. So let's create a variable called subnet so you can see what I mean. So variable subnet. We'll do the type, and we'll start with map. And inside the map is going to be an object. And this won't work as is. The object needs predefined lists. Like if I run Terraform plan, it's going to say, hey, we need some attributes. So what we need here is inside our object, we need another parenthesis. And there I'm making a map, essentially a predefined list. So it's going to be squiggly brackets, and let's hit enter. And in here, I'm going to write subnet position, I'm going to write delegation, and I'm going to write default outbound access enabled. Subnet position is equal to its type. So I'll say number. Delegation is equal to its type. So I'll call it string. Default is going to be a bool. And right now, we basically made all of them required, but not all of them are required, right? Like general didn't have delegation or default outbound. So what do we do there is right before the string, we write optional and then put the string in quotes like that. Same here, optional. I'll put bool in parentheses. Make sure you type it right. Now what optional means is that if a value is not provided for one of these, Terraform would treat it as null. That works perfectly with the try and the null pattern we saw earlier. So essentially we've created a subnet that requires any number of subnet names that are going to be at the map level, but each of those subnets are going to have subnet position for sure, delegation, and default optionally. And just to show you, like if you try to type default here, look what shows up. It gives you an option to write the name of our subnet. So you could have called this general here, and then you can see it has squiggly brackets. And if I do control space here, my only options are the subnet and the delegation. Required, optional, optional. And this is very much similar to how resource blocks and all these other blocks I've been working with are. Let's remove the default and head over to our TF-vars, and we'll write it there. Since the variable has the same name as our local, we can actually paste that exact thing right there. We can just copy this, remove it, and then in our TF-vars, just paste it. And that's it. Terraform FFT, get it all nice and sorted. Now you can see why TF-vars are useful. They make complex variables much easier to work with. And now you have the flexibility to set how you want your subnets to be depending on your environment, whatever job you run, which can differ from different environments, having their own TF-vars, having one set, prod having another set, etc. And let's add another subnet to this. And I'll just call it storage so we can see it in action, position 3. And then one thing we definitely have to do is go to our subnet where it's mentioning our local and replace it with var.subnet. Make sure it's the only place where it's done using Control F. It is var.subnets. Run Terraform plan. And Terraform should try to add only the storage subnet that we added and keep everything else as is. Yep, going to create the storage. Perfect. Let's keep working on variables. Now let's look at our tag locals as well for common tags. Now some of these could just stay here as common tags, but I want 3 of them to actually come from variables because they may change, right? It may not be these owners, it may be somebody else. I don't want to hard code it in locals. I want it to be something from the outside providing it. So we're going to do the same here. So let's create another object variable. This time I want to enforce 3 properties, owner1, owner2, and cost center. And we'll call this mandatory. Variable mandatory tags. And then we'll say type equals object. And then we'll say owner1 string, owner2 string, and then it was cost center. Now what's interesting is we can actually make cost center a number to show that we can enforce data types. Bear with me, even though it's string here. I'll teach another concept shortly. And then what do we do here? Because I want to keep these 2, we could keep that. And then we can just do a merge. Merge, enter, tab, var.mandatory tags, comma, this. So our common tags will be our mandatory tags plus our 2 tags that we're just adding from common tags itself. And let's add our mandatory tags to our df_var file. Just like that. So now our mandatory tags are added by the variable, and our common tags will be just added by our local. These are calculated. I always want it to be this field. I always want it to be calculated to determine the creation time. Now, quick note before we validate these tags. In mandatory tags, I put cost center as a string, but in the variable, I put it as a number. And that is okay. String, number, and bool are called primitive types. Terraform can sometimes convert between them when it is safe to do so. So if I provide a number, a string, but it actually has numbers in the strings, it will convert that for you. The same is true if it's expecting a bool and I provided in a string, true or false, it will accept that as well. But for cost center, I'm going to treat it as a number. So let's take this one step further and add some validation. First, I want to ensure the cost center is within a range our organization expects for our cost center. Then I want to ensure owner 1 and owner 2 look like valid email addresses. I won't go as far as validating them against enter ID, which we should ideally save that for another video. Let's start with cost center. And I'll just write the error message so we don't get annoyed. Let's do validation, condition, this, var.mandatory tags. Okay, let me just write the error message so it doesn't show. I'm going to put 2 of them in here, so I'm just going to paste this. Owner 1 and owner 2 must have valid email address, and cost center must be between 1,000 and 2,000. So you can see where this one is going. So we can say cost center. And notice I didn't use the quotes this time. And var.mandatory tags.cost center less than equal to 2,000. So this will check and ensure that the value for cost center is between these 2 values. If it is, it's true. If it's not, it's false. Now let's add our email validation. We'll start by extending this condition by using and I'll do a new line for our regex pattern, which I'll use next. And I'm just gonna put in quotes here. I'm not going to teach regex itself here. I just want to show how Terraform can use regex inside validation. Since we have 2 owners, let's use a for expression. So what we'll do is all true is 2, because both of them must be true, for email in var.mandatory tag.owner1. And then we're going to put our regex here using a function for regex. Problem is that regex itself does not return a true or a false. If the pattern matches, it returns the matched text. If it doesn't match, it throws an error. So what we want to do is make it a true or false statement. And the way to do that is wrapping it around another function called can. Can just means if you can do it, it's true. If you can't do it, it's false. Not a fail. Terraform format. Move this line. Hopefully I did it right. So now let's check the validation. Now our validation checks for two things. It checks to see if our cost center match is within a range. That is true, great. But it also needs to make sure that both of our emails, owner1 and owner2, are actually an email address and not something that shouldn't be written there. Let's confirm for proceeding. So let's do 5,000 and do Terraform plan. Should fail. Okay, it failed. Perfect. And let's just do 1,000 again and confirm it actually works as is. And it does, right? So if I now remove the @ sign and do Terraform plan, that should also break because the regex pattern is not being matched where it needs to have an @ sign, a .com, or whatever. Cool. That broke as well. Let me show you a few more things, not so programmatic heavy, to end our intermediate episode. Now this file is starting to get long, and this is just a few resources. Now VS Code does have this feature called outline that we saw in the panel, which can quickly navigate areas, etc. But real Terraform operates a bit different. Everything in Terraform is within the context of your folder, meaning we don't just have to make this one main.tf file. As long as in the folder we provide multiple files with the same .tf extension, they all get put together as one big config file for Terraform when you run commands. So we can move a provider to provider.tf, variables to variable.tf, resources you can do network tf, storage tf, etc., or just keep them in main.tf. Completely up to you how you design that. And since my project is small, I will do provider.tf, variable.tf, main.tf. So let's create them. I'll create a new file called provider.tf, and then I'll make another one. We'll call it variables.tf. And then everything that is provider related, which is just these two, I'll move to the provider block. Everything that's variables, these things right here, I'll move to our variable blocks. And then the nice thing about VS Code is you can actually split. So like if you need to compare data from your variables to your main file, you can just do it like this. Or if you just drag it out, you can open as a new window to move to your other screen or whatever it is you want to do. So having multiple files doesn't mean, oh my God, I have to click back and forth. You can have them separated out as two pieces to view at the same time. And just to prove it, if I do Terraform plan now, nothing should change because it's going to read the provider from the provider folder. It's going to read the variables from the variable folder and the main from the main folder, as they're all in the same folder structure, which is Terraform 102. Okay, let's actually run Terraform destroy. You can just type auto approve. And we'll just destroy everything. And let's fix our code a bit. So I had used environment dev for my NSG and my association. Let's make it prod again, as we originally intended. And also, tfvars environment, let's make prod. And our sub ID, let's actually point it to our production ID. Here. Now, while that's deleting, let's talk about something else. So far, everything we've built has lived inside a single Azure subscription. But Terraform isn't limited to just that. A single Terraform project can deploy resources across multiple subscriptions, or simply read information from one subscription while deploying into another. We do this by defining multiple provider blocks. One provider is considered the default. That's the one we've been using this whole time through this episode. Additional providers are given an alias. Each provider represents a different connection to Azure. They can even have their own identities, as you notice they exist within the context of the provider blocks. Then inside the resource or data block, we use the provider argument to choose which provider Terraform should use. If you omit the provider argument, Terraform uses the default provider. If you specify an alias, Terraform uses that provider instead. Since we've been working with networking, let's stick with that theme. And we'll create another VNet in our management subscription. Then we'll peer it with the VNet we've already built. Let's make our provider. So in my provider block, my provider.tf, I'm write provider Azure RM, same as before. In fact, I'll just copy all this. And the only difference is I am hard coding a particular subscription, so I'll actually just write that here. Now, this won't work because they're both the same. What you want to do is say an alias and then provide a name. So I'll say management_sub to indicate that this provider block, if a resource is referencing it, it's going to go to this subscription. I'm not going to provide anything identity related because we're going to use the same service principal we have been using. Now let's head back to our main and say resource Azure RM resource_group RG2 because we already have a resource with RG. Now this is going to create it in the same provider as our default right here. In order to reference this, what you do is say provider, and then look what shows up, Azure RM, and azure.mgmt.sub. So that's the one we want to do. Terraform format. And that's all it takes. This resource will now be deployed in our management subscription. Next, let's create a VNet inside our resource group. I'm just going to paste this because we've sit through this enough. Now I'm still going to provide the provider, even though in the location and resource group name we're referencing this resource. That is not enough. Like if you do this, you're still saying go to the default subscription, but then it's not going to find the resource group there and fail. So you should have provider in there. And what is our goal here is to peer this network with the network that we're going to create in our production subscription. And I'm just going to power through this because who cares? The first peering is created in our default subscription and it points to our management VNet ID. So this is what it is. This is what it's pointing to. And then we have to do the exact same thing because VNets are directional. We also need the reverse peering. And then we'll create exactly the same thing, just flipped. So instead of main to management, it's going to be management to main, and the provider is going to be provided here, and then these two are going to be flipped. And that's it. If I do Terraform plan, it's going to create all of our resources. I trust it, so I'll just hit Terraform apply. Okay, resources have been created. Let's have a look. I'll open my two subscriptions. So there's our management subscription. So this is our corporal management, right? It created the VNet for that. And then if I go to my production, there's our production one where we create the NSG and all that. And then in our VNet, if we look at peering, it has a peering set to our VNet for management. And then the same is true here. It's connected back to our production subscription. Right, and that's as easy as it is to work with multiple subscriptions. You just add the alias, and then now you can work with two subscriptions rather than one. Now that I'm happy with what we have, let's just clean everything up. I'll just do Terraform destroy. That's going to wrap up part 2 of the Terraform series. Now compared to our beginner episode, we covered a tremendous amount. We explored functions, expressions, loops, operators, validation, nested type, dynamic blocks, lifecycle rules, provider aliases, and a whole lot more. There's one thing I hope you take away is that Terraform is much more than simply filling out resource blocks. It is a surprisingly capable language that allows you to build reusable, dynamic, intelligent infrastructure. The goal wasn't to show how complex your Terraform should be. The goal was to show just how complex Terraform can become when you start treating it like a programming language. Which brings us to an important engineering principle: KISS versus DRY. KISS stands for keep it simple, stupid. In other words, don't introduce complexity when you don't need it. Did I need to loop over 3 subnets? Probably not. Did using a dynamic block for the NSG help? Maybe, but we're only applying it to a single NSG, so why bother? If we're deploying dozens of NSGs, the abstraction could make a lot more sense. On the other hand, dry means don't repeat yourself. We abstract common patterns so we don't have to write the same thing over and over again. The danger is taking dry too far. Imagine coming back to this project 6 months from now. You'll be jumping between resources, locals, and variables trying to piece together how everything works. Your colleagues will probably hate you for some of the abstractions that they have to deal with it. So in real projects, I don't use every feature simply because it exists. I try to find the right balance between KISS and dry. keeping the code maintainable, readable, and clear, while only introducing abstraction when it generally solves a problem. Either way, thank you for watching. I'll see you in the next one.